Hello everyone. Today I will present self-checking deep neural networks in deployment. Deep neural networks are now used in a variety of domains. The power and accuracy of DNNs have led to developments of deep learning systems in safety and security critical domains, including self-driving cars, malware detection, and aircraft collision avoidance systems. Such domains have a low tolerance for mistakes. Unfortunately, the stochastic nature of deep learning virtually ensures that deep learning models will not achieve 100% accuracy, even on the training dataset. Just as our community has developed effective techniques and mechanisms to monitor and check programmed components, we believe it is now necessary to do the same for DNNs. Since in mission-critical applications, a wrong DNN decision could be costly, we believe that such applications must include logic to first check the trustworthiness of a DNN's output and then raise an alarm when there is low confidence in the output. We thus aim to build a general-purpose system that monitors a deployed DNN's predictions during inference, raises an alarm if there is a low confidence in the predictions, and provides an alternative prediction that we call an advice. We call the proposed technique SelfChecker. The following are the challenges. Firstly, how to evaluate or quantify the trustworthiness of a decision. Secondly, when the model's decision is not trustworthy, how can we construct accurate advice for an alternative predictions? This figure presents a motivating example. The top of the figure depicts the architecture of a convolutional neural network with 3 convolutional layers that classifies digital images. As we can see, even though the softmax decision probability is high for input 6, the model decision is still wrong. The 2 rows of images at the bottom of the figure depict attention heat maps for the associated layers when given test inputs for digits 3 and 6 respectively. To visualize where the features of each layer focus, we apply grad cam to highlight the attention heat map on the original images. The heat map images show that different layers have different points of focus, but some of these focus on a particular part of the image and may be misleading. For example, the second and third layers for 6 are different from the final prediction. If SelfChecker considers the outputs of these layers, it can detect that the model is not confident about the final output. Although the CNN misclassifies the second image, in both cases, the images appear to be recognized correctly by 1 or more hidden layers. This example thus illustrates the promise of using layer features to check the model's classification of a test instance. Therefore, our key insight is that the more intermediate layers match the model's prediction, the more trustworthy the model's prediction. Then we detail our proposed technique SelfChecker. The goals of SelfChecker are firstly to check a DNN's prediction, secondly to raise an alarm if the DNN's prediction is determined to be incorrect, and finally to provide an advice or an alternative prediction. SelfChecker's training module is used after the model has been trained to configure SelfChecker's behavior in deployment. Given a DNN model M trained on training dataset and validated on validation set, for each layer in M, SelfChecker first computes layer-wise density distributions of each class using kernel density estimation. Based on the distributions, SelfChecker can estimate the density values of each validation or test instance on each class. The higher the values of the class, the more similar the features of the instance in this layer are to the specific class. After SelfChecker obtains all of estimated density values on validation set across all layers, SelfChecker finds the optimal layer combinations to reach the best alarm and advice accuracy. SelfChecker's deployment module runs along with the inference process. It analyzes the internal features of a DNN when the model is given a test instance and provides an alarm as well as an advice if it detects an inconsistency in the model's outputs. To detect these inconsistencies, the deployment module uses the density values and the specific layer combinations based on the configuration supplied to it by the training module. Note that although SelfChecker analyzes the features extracted from the internal layers of a DNN, the training module is independent from the architecture of the model and requires no model modifications or retraining. The deployment module, however, is specific to a DNN. Then we talk about the experimental results. This figure presents the alarm accuracies of 3 deep learning models, Combinate, VGG16, and Resonate20, in deployment on 4 datasets, MNIST, fMNIST, CIFAR10, and CIFAR100, checked by SelfOracle, Detector, ConfidNet, and SelfChecker, and the alarm accuracies of 2 self-driving car deep learning models, checked by SelfChecker and SelfOracle in terms of F1 score. These left 4 are traditional DNN classifiers. As we can see, SelfChecker has a higher F1 score than all competitors. It correctly triggers an alarm on over half of the misclassifications. In self-driving car scenarios, SelfChecker triggers more correct alarms than SelfOracle for 2 DNN models with comparable false alarms. We thus conclude that SelfChecker effectively triggers alarms that predict misbehaviors of deep learning models in deployment with high true positive rate and low false positive rate. This figure compares the accuracies of the original model M to those of M having advice provided by SelfChecker. Our results show that even though the trained deep learning models have achieved state-of-the-art accuracies, the advice can still improve models' prediction accuracy for datasets with 10 classes, but decrease the prediction accuracy for datasets with 100 classes. There are 2 reasons for this. First, finding a correct prediction from 100 classes is a harder problem. Second, the validation set per class is more limited. CIFAR10 has 1,000 samples per class, but CIFAR100 only has 100 samples per class. We empirically find that SelfChecker's advice can improve models' prediction accuracy when the number of samples per class is over 200. We showed that the SelfChecker's advice can improve the accuracy of the original models beyond their state-of-the-art performance with a sufficiently large validation dataset. Therefore, we conclude that SelfChecker outperforms state-of-the-art approaches on detecting more unconfident decisions and generating more correct alarms and advice. To summarize, in mission-critical contexts, DNN outputs must be closely monitored, since they will inevitably make mistakes on certain inputs. We develop a SelfChecker, a self-checking system that monitors DNN outputs and triggers an alarm if the internal layer features of the model are inconsistent with the final prediction. SelfChecker also provides advice in the form of an alternative prediction. The last one is the GitHub repository of our released code. We have many additional details, including other evaluation results, in our paper. We encourage you to take a look at it. That's all. Thank you for your attention.
Thank you again for joining us in the Q&A for the self-checking DNN paper that we are presenting right now. We have two of the authors in the backstage, and they will be very glad to answer your questions. Some of them are already in the chat, so please go ahead when you wish.
Okay, maybe about the first question related to the test metrics such as LSA, DSA, or uncertainty to detect misclassification of data. Not yet, but this indeed a great direction, but not the focus of of this paper. So we actually focus on the in the deployment period. So we haven't tested this part. And the second question, did you consider the SelfChecker for the problems outside the computer vision domain? Actually, as we also mentioned in the paper that actually we use the intermediate layer information to this is the base of our proposed approach. We didn't limit it into a specific domain, for example, the computer version domain. It can be also used to RNN, since we can unfloat the RNN into a forward network. So actually, it can be used, but we haven't. But we didn't show in this paper. The results can be. We will show the results in the future. The third, then the question.
That is the third and fourth question.
By the way, I didn't see the questions on my console.
If you don't see the questions, I can read them aloud. The next question is, do I understand correctly? Is your work trying to infer an answer when omitting the last few layers of DNN?
Yeah, actually we didn't. Actually, we didn't omit the last few layers. We consider all the possible layers. Internal layers, especially for the activation layers. So actually, we also try to select proper layers from all the total layers. So it is not specific the last layers.
How efficient is your technique? Is another attendee asking.
Yeah, we actually also compared the time consumption in our paper, and yeah, it is not the best, because there are two competitors. They only use they design another DN models to answer to answer the questions. We actually spend more time than these two competitors, but the accuracy of these two competitors are not that good. But compared to the best competitor, actually we spend less, very less time. And the last one, do you have any result regarding model's original layer fix? For example, if a model's number of layers is small, the detection advice is not effective. Or yes, actually, indeed, this is our limitation for the very narrow. Narrow network. That means it only has, for example, 4 layers, something like this. But actually, we consider it is not that deep, so it is not deep narrow network. So this is not our focus of our paper. Yeah, thank you.
While we wait for some more questions, and I invite the public to make them, okay, I'm curious about something. It's not clear to me. Is your method, your proposal, completely automated, or does it need any preparation step before you start analyzing the inner layers activity?
Yeah, it's totally automatic. It doesn't need any human interface. If we, sorry.
No, please go ahead. I was thinking.
Actually, we only need to prepare some configurations during the training period. Then after that, in deployment, actually we design our technique using the the configuration obtained from the training process. For example, which layers should we select, something like this. So we don't need human interface.
So in terms of let's say time cost, for instance, it does not imply any overhead.
Actually, as I just mentioned, actually the time consumption is acceptable, but we also agree that it still have some room to improve. Because actually in deployment, the time is very, a strict, a very strict problem. So we indeed will have will do more research in this part. Yeah, but until now, actually, the time consumption is acceptable. We only take around 30 seconds. Yeah.
And in terms of practical applications, have you considering to put this in practice in industry, or do you have any application in mind that you want to improve with your proposal?
Yes, actually, we also tested it in the dataset, self-driving car dataset, and we outperformed the state of the art. Applied in the self-driving cars. So this one will be one possible, application. But actually, there are still many other choices. For example, the medical image diagnosis and the air screen. Air security screening, something like this. I think it can also be a possible applications.
And future areas of research, how do you plan to continue with your research? What do you plan to study? Which sides of the research has not been solved yet, and you want to continue through those areas?
Yes, actually,
sure. Go ahead.
Yeah, just as mentioned by the audience, actually, indeed, until now, our research areas, experimental data set used in our paper is related to computer version. This specific domain, and we plan to go on exploring the possibility to other, for example, and something more specific, and also complete areas. Yeah.
Well, we still wait for public questions. If you have them, well, yeah, have another one.
Extracted from that can be regarded as a feature of the input to detect and predict. Yeah, yes, I agree. I also listened to the, other papers just now. Yeah, indeed, it could be a possible future research direction. Thank you for your suggestion.
Well, it's 50 seconds to finish, so I think that this time we will finish orderly. I think this is the last presentation of this block. We will have a break afterwards, but in what regards this paper, remember that in a few seconds this pop-up with join the discussion room will show up, and I encourage you to, those interested of course, join the discussion room with the authors. It will not be live streamed, that is, the discussion room is completely private, and you will not have to make questions through the chat, but you will be able to talk freely using the camera and the mic with the authors. Okay, the same way the previous presentations, the two previous Q&A are probably in the discussion rooms. So thank you very much, and see you soon.